Okay, so we are continuing on in our foundation of stat mech. So today we're going to be covering the Boltzmann distribution. And hopefully we'll get to the definition of the canonical partition function. And these two are pretty closely related. Yes? Oh, screen. So the partition function in stat mech is everything. Once you have the partition function, you can solve all the problems that you need to solve in stat mech. But it is this weird, obscure, kind of abstract concept. So we're going to derive one particular partition function, and then in the subsequent days, we're going to be manipulating it for different types of systems. Okay, so to derive the canonical partition function, we're going to do a very similar approach to what we did in classical thermo. We're going to define sort of an arbitrary system. In this particular arbitrary system, we are going to have two isolated subsystems, A and B. And they're going to be surrounded by an infinite reservoir. Right, basically the universe, the galaxy. We're going to say this reservoir has constant properties. In a true sort of stat mech derivation, we don't know what that constant property is, but we're going to jump the gun and just say that the temperature is constant. So the only way that these two systems can be related in any sense is that they share the same temperature. But apart from that, they are completely 100% isolated. So a couple of nomenclature. P of A for E of N is going to be the probability that subsystem A is in a state with energy En. And then conversely, PB, we're going to use En. So note that these are energy states. It is a particular exact snapshot description of the system, not energy level, which of course you'd have to times it by the degeneracy. And we'll come back to that in a little bit. But this is a particular energy state. So for the combined system, so if A and B are in particular energy states, it makes sense that if we have the probability of subsystem A being in some state with energy En, probability of subsystem B being in some state with energy level Em, is going to be equal to the combined probability that system A is in some state, system B is some state, times those together, that gives you the total probability that the entire system is in that particular configuration. And we're going to write this as EAB, where this is equal to En plus Em. Just like if we imagine with dice, right? You roll one die, you roll the other die. The combined probability is the 1 times 6 and the 1 times 6. So for any particular unique dice roll, you're going to have a 1 in 36 chance of getting it. Of course, there's different ways you can add up to 7 and 5 and things like that, but the general rule holds true, right? Okay, so what we're going to do now is we're going to manipulate these probabilities and see if we can find any properties that are relating subsystem A to subsystem B. So to start off this approximation, we're going to assume that the energy levels between each different step are very, very small. Right, so we're going to assume that the different discrete energy levels, right, we know from quantum mechanics that they are discrete individual energy levels. But we are going to assume that it is a continuous distribution. And this is generally going to be an okay assumption, right? If we recall, Planck's constant h is on the order of 10 to the minus 34. Right, that is the minimum quantized energy level based on quantum mechanics. Whereas the Boltzmann constant, which is going to be relating the kinetic energy of gases, the temperature of gases to their kinetic energy, is on the order of 10 to the minus 23. So basically 1 trillionth of an energy difference. So in general, that's going to be a fine assumption. Let me go to the next slide. So what we're going to look at is we want to know how does the total system configuration probabilities change by just changing one of the energies of one of the subsystems. This is going to be exactly equivalent as this, because these are equivalent. A little bit of calculus. Oops, get rid of that. So in this case here, we use the chain rule to expand on this. And we also want to note that d En plus Em d En is just equal to So again, with these types of derivations, they didn't happen overnight. So these were a lot of trial and errors I believe by Boltzmann did all this work. So it'll all make sense in just a moment. So if you apply the same kind of logic to the second equation, which we know the two are equivalent, and again here this one is from the chain rule. So basically it's first times derivative of second, second times derivative of first. One of those happens to go away because En is not at all related to Em. That's what that expression is saying. In essence, what's happening here is we are saying in this equation that subsystems A and subsystems B, their probabilities are not at all linked at all. I can independently change A, I can independently change B. This equation here tells us that they are linked, but through the property of the reservoir. The combined probabilities of A and B influence the properties of the system. Okay, so if we put this together, basically this equation here is equivalent to this equation here. And we can also repeat, but using the change in system B and its energy Em. Now, when we do this approach, this equation is going to be exactly the same. And this one here, all you're going to be doing is changing out A for B and N through M, right? So A goes to B, and En goes to Em, but it's exactly the same procedure. So from that approach, we can write now we can relate subsystems A and subsystems B. And we're almost there. So we can rearrange this expression to get all the A properties and all the B properties on their individual sides. And we can combine them using log properties. And this is a form of an equation that we've seen many, many times over again. So we can rewrite it dln PA. So what we have here is a partial differential equation. How does one solve a partial differential equation like this where you can completely separate the variables? I just gave it away. Separation of variables. So the key thing to recognize that these are all related by some constant. Right? All the properties associated with subsystem A and energy En are 100% isolated from the properties of subsystem B with energy Em. So the only way that this equation can hold true is if they're equal to a constant value. In this case, I'll briefly call it K, but then I will actually, for the sake of history, we write this as negative beta. Is there anyone familiar with the stat mech variable of beta? You seen it before?
Yeah.
What is it?
It's 1 over kBT.
Exactly. So this is actually minus 1 over kBT. So many times it's actually easier to work with beta than it is in temperature for the derivatives. If you recall all the way back from early on, we defined 1 over temperature as ds du at constant v. So the temperature isn't necessarily the easiest one to mathematically work with. So this beta variable is exceptionally convenient for stat mech and a lot of sort of molecular type interactions. Okay, so all we need to do is integrate this partial differential equation. But it is not bad at all. Just about the easiest PDE you could ever hope to solve. It's just an exponential function. Now we just need to solve for the constants of integration. And for that, we rely on probability. We know that the system has to exist in some state. So no matter what, yes, question?
I haven't answered that plus means and.
Yeah, it's an and, yeah.
Okay.
That's my notion for that. So we know that the probability of all states has to be equal to 1. The system has to exist in some state. Because in theory, we have a way to organize and categorize and have a classification for all the different possible states in the system. So when we add up all those states, if we've done our job correctly, it'll have to add up to 1. Because we've kept track of every single one of the probabilities. So this is mirrored with B, but basically we know that the constant of integration is equal to the summation of all the different states. Okay, and now we're through the worst of it. So we are going to now define Q, which we write as N V beta, or Q is N V T. This is equal to the canonical partition function. And we write it as Q is equal to the summation So now we can write that the probability of any system, I'm just trying to use E alpha so we don't have to say whether it's A or B. Okay, so as a recap, P of I is the probability that the system is in state I with energy E alpha. This term in the numerator, this is what we call a Boltzmann factor. And you may have encountered this before in your research or maybe undergraduate research or studies. But basically what this tells us is that as the energy increases of your system, the probability decreases. It's an exponential decay, in fact. So if you're trying to figure out which of the two systems is a more likely one to be in, the higher the energy, the less likely it's going to be in that particular system. Conversely, as the temperature increases, beta will decrease because it's a reciprocal of it. Therefore, the probability goes to 1. Right, because e to the 0 is equal to 1. Sorry, not probability. The probability will go to 1 over the partition function. So what this tells us is that as you go to an infinite temperature, all states are equally probable. It doesn't tell us that as you go to an infinite temperature, the system is always in the highest energy state. That would violate the second law of thermodynamics, right? Because you would go from a system where you have randomness and you have different particles in different states, but if you went to an infinite temperature and you had everything in the highest energy state, you would basically have the same entropy as absolute zero. Right, so this tells us fundamentally how different systems behave. At high temperatures, everything is equally probable. There isn't a more general rule than that. So, what we're going to do now is we're going to play around with this relationship here regarding the probabilities. Any questions so far on how we got here? It's a tad bit mathematically convoluted, but essentially what we're trying to do is relate the changes in energy of subsystem A and subsystem B to the total system configuration. And the only way that we could do that was through the thermal reservoir properties, which as it turns out was a constant temperature. Okay. So what we've been looking at now is the probability in being in some state with some energy level. But recall, we can also write that the probability with no subscript of the system having some energy level of E alpha is going to equal to its degeneracy of that energy level times by the probability of it being in that. So if we'll say here there's no subscript I. So we're talking about probability of energy level E alpha. This is the degeneracy. And from the equal a priori hypothesis, right, any state with a particular energy has to have the same probability. So if we just look at the probability of one state with one energy E alpha, if we times that by the degeneracy, how many different ways can the system be organized in that configuration? That'll give us the probability that the entire system has that energy level, which is this term on the far left. Right, if you recall, we had that Lx, Ly, Lz. Each of these correspond to different energy states, but they all have the same energy level. This could be state 1, this could be state 2, this could be state 3, but their energy level was all the same, because it was the summation of L of I squared. From last lecture. Now this is for a particle in a 3D box. So if we really go back and we say, okay, what is the probability that we have any state that has the energy level E alpha, right? No subscript of I. This is going to be equal to the degeneracy of that level times by the probability of being in that particular any state with that energy, divided it by the partition function. Oops, no, sorry, that's not right. This is equal to that. So we're going to take a look at how this equation would apply for an ideal gas. So let's assume that we have one helium atom. It can have velocity Vx, Vy, Vz, or momentum Px, Py, Pz. And let's assume that the velocity levels can only be integers. Right, so this is sort of a combination of the quantum scale and the continuum scale, right? So as the velocity increases, the energy increases as well. As we increase the energy of this particular particle, the number of ways that I can come up with some number by adding up Vx, Vy, Vz for an absolute velocity increases, right? If I've got a velocity of, let's say, 1, That means it can either be Vx is 1, Vy is 1, or Vz is 1. If I have a velocity of 2, there's only so many ways I can do that, and so on and so forth. If I have a velocity of 1,000,000, well, there's a ton of different combinations that I can get to organize that. But as I increase that, my energy also increases. Right, so we're balancing out the degeneracy, the number of ways the system can be in a particular organization, with the energy. The higher the energy the system is in, the lower the probability. So if you look at that graphically, as we increase the energy, we look at the probability of being in some state I with energy alpha. This is going to be some sort of an exponential decay. If we look at the degeneracy, it's going to be increasing as a quadratic function in this case. And so when we combine the two, you get some probability distribution. And this is the Boltzmann distribution. Also called the Maxwell-Boltzmann distribution. So when we're looking at a box or a jar of gas, not every single gas molecule has exactly the same velocity. They follow the Maxwell-Boltzmann distribution of velocities, which in its core is a distribution of basically weighting. The high energy particles have a lot of different ways that they can have that energy distributed in Vx, Vy, and Vz velocities, but the higher energy the particle is, the lower the probability it's going to be in existence. Right? So that the mean or most likely velocity of a gas molecule isn't necessarily going to be the highest energy state or going to be the lowest energy state, for example. It's going to be some balance between the number of ways you can configure the system and the energy of that particular configuration. Good so far? Okay. Now we can actually really get the cool power of the partition function out. So we are going to relate the canonical partition function. Right, and recall that Q, N, V, theta is equal to the summation of all the states I scaled by a Boltzmann factor. Now this particular partition function is for constant n number of moles, constant V, constant volume system, so rigid walled system that's not permeable, and at constant temperature. So what, based on these variables, would we expect from macroscopic thermo would be the property that's most intimately linked to this? Is it Gibbs? Is it Helmholtz? Is it... What if I said it was an NPT system? That one's enthalpy.
This one's Helmholtz. This for-
That would be, so Helmholtz is for open systems. Helmholtz and Gibbs are for open systems as well. For the closed systems, this is going to be related somewhat to the internal energy. Entropy is generally related to an NVE system. So we're going to say the internal energy is going to be equal to the average energy. And this is really common notation you'll see, the brackets being an average. So we can write that by saying we're going to take a weighted average of the energy and timesing it by its probability. So this term here, right, this is the probability of being in state I with energy EI. So all we're doing is we're taking a weighted average of all of the different possible system configurations and timesing it by their energy. Yeah.
In the Boltzmann distribution, that is EI, not.
Oh, yeah, this is just my sloppy handwriting here. So this is just a weighted average of the possible energies times by their probabilities. So if we also note, I mean, exponents are really kind of easy to take derivatives with. If we look at the derivative dq d beta at constant n and v, which is exactly the system configuration that we're working with, we have an equation that can relate between the microscopic length scale about the total number of states, which is Q in the canonical partition function, to the internal energy. So the partition function is a abstract concept. And the tricky thing here is that we are now taking a discrete summation and treating it like a continuous function, which is generally going to be the approximation we'll take throughout the stat mech in this class, unless it's sort of a unique circumstance. But basically what stat mech is now providing for us is if we can dictate how a particular particle will behave, then if we add up every single possible way that that particle can move around, rotate, vibrate, translate, and we sum up all of those different states, that's the partition function. Right? As soon as we scale it by the Boltzmann factor, that's our partition function. Once we have the partition function, then we can then relate it back to macroscopic properties. And so what we're going to be doing on Friday and next week before the exam is we're going to be taking different partition functions and then re-deriving new relationships. How do we get the pressure from the partition function? How do we get the entropy? How do we get the heat capacity? Right? So once we have this relationship here, now we can start to lean on what we already know about classical thermodynamic systems. But the key thing to keep in mind here is that Q, the partition function here, is a weighted summation of all of the different possible configurations of the system. It is a statistical sort of combination of everything. But when you actually do this infinite summation, we'll see, it'll actually converge to a real number, which is kind of weird. You could actually plug in variables and the partition function gives you a number. But that's because what we'll be doing is we'll be converting a summation to an integration. And that's the math that we'll be working on throughout StatMech. Does this make sense? So of course the first thing we're going to be working on is an ideal monatomic gas. So we'll be taking the particle in a box, applying the same procedure that we did here for an arbitrary system, right? We'll actually have a function that tells us what is the energy as a function of certain properties. Then we'll add up all of the different configurations, take the derivative of it, and we'll get the internal energy. The result will be what you expect it to be, 3/2 RT or 3/2 kBT, but we'll show how we get to that point. Okay. That's all I have prepared for today. Any other questions? All right. See you on Friday.